Hello and welcome to 50 conceptual questions and answer of video series. In this video series, I will talk about 50 conceptual questions and their solutions in details. This video series will be specifically helpful for those students who are preparing for different kind of competitive exam, including GRE physics, and it will be also helpful for BSc third year student and MSc student. So without wasting any further time, let's jump in. So here is the first questions, and in this questions it has been asked, a thin square plate carries a uniform surface charge density sigma. The potential ratio at the center and one of its corner is 2 times, or it will be 0.5, or it will be 0.25 or 1. So what has been asked in this question, let's say we have a square plate and this square plate carries a uniform surface charge density sigma. Uniform means this charge will be independent of position anywhere on the surface. If you take a unit area, each unit area the amount of charge will remain same, so it's constant over the surface. And let's say the side of the square plate is A, and if we calculate the potential at the center of the square plate, and since charge is uniformly distributed, so each corner will have same potential. So if we calculate potential at any of this corner, let's say on this corner, and if we assume that let's say potential at the center of this plate is VO, and potential at the corner is VC. So in this question, it has been asked that if we calculate these two potential, that is potential at the center and potential at the corner, and then if we take the ratio of these two potential, V0 by Vc, so what will be this two ratio of these two potential? So I hope questions is clear to everyone. Let's proceed to solve this problem. To solve this problem, let's consider a two-dimensional rectangular coordinate system in such a way so that the center of the coordinate system coincide with the origin of the coordinate system coincide with the center of this square plate, and sides of this square plate are parallel to this x-axis and y-axis, and this plate dimension, let's say side of the square plate is, let's say, A. So then we have to calculate potential at the center of this plate. To calculate this potential, first consider a point on this plate. Let's say this point have coordinate with respect to this origin, x and y. And then since it is a continuous charge distribution, to calculate the potential, we have to consider elementary area. So in this case, since it is a two-dimensional plate, so we can consider this elementary area ds is equals to dx and dy. So then since the charge is uniformly distributed over the surface, so it doesn't matter where we are taking this point, everywhere the charge per unit area will remain same. And and this elementary area is a very small area, and so charge on this elementary area will be like as a point charge. So what we can do to calculate the potential, first we will write the potential at the center due to this small elementary part, and then we can integrate over the surface to calculate the potential due to whole surface. So let's say if V0 is the potential, at the center of the plate, then V0 can be written as V naught is equal to 1 by 4 pi epsilon naught, and then charge on the elementary area, that is sigma into ds, and in this case ds is equals to dx and dy. And then we have to so this charge on this elementary area behave like as a point charge. So if we write if we want to write the potential due to elementary charge that is lies on this elementary area, so we can behave like, we can choose like in this way, the charge that will lies on this elementary area, it will be point charge. So we can simply write the definitions of potential due to point charge. And what is that definition? The definition is 1 by 4 pi epsilon naught, and then charge, amount of charge, and divided by distance of the point where we are calculating potential from the position of charge. So in this case, this elementary area and the distance between the elementary area and the center of the plate can be written as x square plus y square square root. So this is the potential due to this elementary area. And now if we want to calculate due to the whole plates, what we have to do, we have to integrate over this surface. So we have to put the limit of this integration. So for whole surface, since we have considered that the center of the plate and the origin of the coordinate system are at the same point, so and the sides of the plate is a, so this limit of x and y will be minus a by 2 to plus a by 2, and similar for y also, minus a by 2 to plus a by 2. Okay, so if we calculate this integration, then we'll get the potential at the center due to whole plate. And similar way, if we want to calculate potential at one of this corner of this plate, so again we can assume coordinate system. Again we are considering rectangular coordinate system, but in this case we are considering that let's say origin of this coordinate system are at one of the corner of this plate, and again the side of the square plate is parallel to the axis, and let's say this is x prime axis and this is y prime axis, and side of the square plate same as it was previous, let's say. So again, since charge is uniformly distributed, continuously distributed, so we have to calculate the potential. First we have to assume a point on the plate. So there, this is the point, and let's say the coordinate of this point with respect to this origin is x prime and y prime. And then if we consider elementary area around this point, and in this case we can write this elementary area ds prime is equals to dx prime and dy prime. And similar way as we have written here, so if we want to write the potential at the corner of this plate, and if we assume that say if Vc is the potential, Vc is the potential, Vc is the potential at the corner of the plate, then Pc can be written as Vc is equals to 1 by 4 pi epsilon naught, and then charge on the elementary area sigma into elementary area, in this case dx prime and dy prime, and then the distance between the origin and the point In this case, it will be under root of x prime square plus y prime square. So this is the potential of that charge which lies in this elementary area. So now if we want to calculate the charge due to this whole plate, so what we have to do, again we have to integrate this integration over the whole surface, and for the whole surface in this case we have to put again this integration limit, and in this case this limit will be, since here you can see this is the origin, so x will be changed from 0 to a and y will also be changed from 0 to a. So both x and y limit will be 0 to a and 0 to a. So if we calculate these two integration, we'll get the potential at the corner and potential at one of its potential at the center and potential of the corner of the plate respectively. But in these questions, it doesn't ask what will be the potentials at the corner and at the center. It has been asked what will be the ratio of these two potential. So this type to calculate this integration will not be easy. So that's why actually in this questions it has been asked what will be the ratio of this potential of these two point. And you can see that both the function almost similar, only thing is different here that limit are different. In one case it is minus a by 2 to plus a by 2 and another case it is 0 to a. So somehow if we can change this limit and make a identical limit for both the integration, and then since function is almost same, so we can just, if we take the ratio, then this two integration will cancel out each other and remaining part will give you the correct answer, what will be the ratio of these two potential. So for that, what we have to do, we have to change this limit first. So how we can change this limit? For that we have to consider another variable, or we have to replace this x and y with another set of variable in such a way so that in both the cases limit become identical, and then we can take the ratio. So what we can do here, if we in first case if we replace this small x and small y by this capital X, where capital X is equals to 2 times of small x divided by a, and capital Y is equals to 2 times of small y divided by a, capital X equals to 2 times of small x divided by a, and capital Y is equals to 2 times of small y divided by a. Then if we put the limit of these two, then it will be changes in this way. Let's say make a table for x and y. So this is for x. First write small x and then write capital X. So when you put this lower limit in this integration, lower limit it minus a by 2. So if you put minus a by 2 in this equation, the capital X equals to 2x divided by a, so what you will get, a minus 1. So when x equals to minus a by 2, then capital X will be minus 1, and when small s equals to plus a by 2, the capital X will be 1. And similarly for y, small y and capital Y, so when x equals to y, small y is equals to minus a by 2, then capital Y will be minus 1. And when you put y is equals to a by 2, then capital Y will be plus 1. Okay. And similarly for second case, we replace this x prime, small x prime, by a capital X prime in such a way so that the limit of these two integrations become equal. So for that we can consider x prime is equals to x prime divided by small x prime divided by a, and capital Y prime is equals to small y prime divided by a. So again you make a table for this x and y, capital X prime and y prime. What will get? Let's say capital X prime divided and x prime table. So in second integration, limit was from 0 to a. So when we put small x prime, no, replace this thing first. Here write small x prime, and here you write capital X prime. So when x prime is equals to 0, then if you put this here, x prime is equals to 0, what you will get? You will get capital X prime is will also be 0. And if you put x prime is equals to a, then capital X prime will be 1. And similarly for y prime, it's capital Y prime and small y prime. So small y prime and capital Y prime. So when you put small y prime is equals to 0, capital Y prime will also be 0. And when you put a small y prime in this equation a, then capital Y prime will be plus 1. Okay, so this will be the new limit of the integration. And we have also replaced this integration. For first integration, we'll replace by this variable capital X and capital Y. And in second integration, we'll replace small x prime, capital X prime with this, small x prime and small y prime with this capital X prime and capital Y prime. So when you replace this when you replace this above integration with these two new variable capital X and capital Y, what you will get this V naught is equals to 1 by 4 pi epsilon naught, and then now your integration limit will be minus 1 to 1, and y will also be minus 1 to 1, and then sigma. And now we have to replace this small x by capital X, and also we'll replace this small by capital Y. So when we replace this, so for dx, small dx, we have to write a by 2 into capital dx, and for small y we have to write a by 2 into capital dy. And then in numerator also we have to change this x and y by the capital X and capital Y. So here it will be a square into capital X square divided by 4 plus a square into capital Y square divided by 4. And then if we simplify this, what we'll get? We'll get 1 by 4 pi epsilon naught. Sigma is constant, you can take out from this integration, so you can write sigma divided by 4 pi epsilon naught. And then denominator we have a by 2 here, a by 2 here, and sorry, numerator we have a by 2 here and a by 2 here, and denominator in this case both the x and y term, it is a square by 4, here is also a square by 4, so we take common. So when you take it out from this square root, so it will be a by 2. So from numerator denominator 1 a by 2 1 a by 2 will cancel out, so remaining there will be one term, so that is a by 2, and remaining other term will be as it is. So minus 1 to 1, minus 1 to 1, and then capital dx, capital dy, and under root of capital X square plus capital Y square. Okay. And on the other hand, if we replace that second integration by x prime, capital X prime and y prime, then what we'll get? We get v naught c, or vc is equals to 1 by 4 pi epsilon naught, and then limit will be in this case 0 to 1, 0 to 1, and then charge density is sigma, and now we have to replace this small x prime with a capital X prime and small y prime with a capital Y prime. So when you replace this x prime y prime by capital X prime and y prime, so we'll get here k into capital dx prime and a into capital dy prime divided by under root of a square capital X prime square plus a square capital Y prime square. And then if we simplify these things, what we'll get? We'll get sigma, you can again take it outside, so sigma divided by 4 pi epsilon naught, and also you can take out this since here x prime and y prime both have another term, a square term, so you can take a square common from the denominator, and if you take it out from the square root, you will get a, and then numerator also have a square term, here is a, here is a, so 1a will cancel out, so here I will get simply a into integration limit 0 to 1, 0 to 1, capital dx prime, capital dy prime divided by under root of x prime square into y prime square. So still this limit is not same. So what we can do to make this limit same, here you can see that function we have to integrate for first integration, it is 1 by under root of x square plus y square. So this function again with respect to x and with respect to y, it's a even function, because if you replace this x with a minus x, it will give you same thing, because here it is function of x square, and similarly for y it is also function of y square. So if you put y is equals to minus y, again it will give you same function, it will repeat the same function. So in this case this function is even, so we can replace this limit minus 1 to 1 for by another limit, that is 0 to 1, but that time we have to multiply with 2. So for x it will be multiplied by 2, and for y it will be multiplied by 2. So finally this integration will be sigma divided by 4 pi epsilon naught a by 2 And then for x and y will multiply 2, so if we multiply 2 times, that means 4 times, and this integration limit now it will be from 0 to 1, 0 to 1 dx dy divided by under root of capital X square capital Y square. And so now look at this two integration. If you integrate this first integration with respect to x and y, where both the limit is 0 to 1, 0 to 1, and if you integrate the second integration with respect to x prime and y prime, here is also limit from 0 to 1, 0 to 1, so both the integration will give you the same answer. So now if we take the ratio of these two integration, so what we'll get? V0 divided by Vc. If we take the ratio of these two integrations, so these two integration will cancel out each other, and then sigma by 4 pi epsilon naught, here also sigma by 4 pi epsilon naught, they will cancel out each other. Here is a, here is a, they will also cancel out each other. So only there will be one factor, and that is 2. And that will be your answer, that the ratio of V0 by Vc, it will be 2. So correct answer will be option A. Okay. So this is a standard way how we can solve this type of problem. But if this type of problem is asked in the any competitive exam, and if you follow this standard method, it will take long time. But in competitive exam, you have to solve more number of questions in a certain time boundation. So instead of following this long method, what you can do, you can consider we can solve this type of problem another way. So to solve this problem in another way, what we can we have to know that at least we should have idea about the superposition principle of potential and superposition principle of charge. So again here we have this square plate whose dimensions is A, and it has surface charge density sigma, and let's say total charge will be sigma into A square, and for we assume it, let's say Q, total charge is Q. So now if we calculate this potential at the center, according to dimension analysis, we can write potential at the center V0 is equals to some constant and then divided by total charge on the body divided by characteristics length of this body. And this constant actually will take care of the shape of the plate. If it is cubic or if it is square or if it is a spherical shape, then this K will be different. And if we consider the potential at the corner is Vc, then to calculate the ratio of these two potential, what we can do, we can put this, we can consider 4 identical square plate like this, and if we put them side by side in such a way as I have shown in this figure, then you can see that it will form a big square plate of side 2A. And each plate is carrying charge sigma. So this whole big whole big plate will have total charge Q prime is equals to 4 times of capital Q. So in this case, if I want to write the potential at the center, so let's say V0 prime is the potential, V0 prime is the potential at the center of the big plate, Then this V naught prime can be written as according to this definition. So we have a square plate. The total charge on this plate was Q and the side was A. So we have written V naught is equal to K, some constant divided by total charge divided by side. So same way if I write K into total charge for the second case, it will be capital 4Q divided by, now this length of the square plate is 2A. So I have to write it 2A. And according to superposition principle of potential, so this potential will be equal to the potential at the corner due to this 4 plate. So look at this corner, look at the center of the big square, which will be exactly a corner of 4 identical cube. This plate, this plate, this plate, this plate, they have sharing this point with themselves. So and each plate at the corner have potential Vc. So according to superposition principle, I can write potential due to this plate is Vc, potential due to second plate is Vc, potential due to third plate is Vc, and potential due to fourth plate is also Vc. So we can write 4 times of Vc. And then from this definition, if we replace this K capital Q divided by small a by V naught, that is potential at the center of the small plate, then what we'll get? We'll get 2 times of V naught, that is potential at the center of the small plate, is equals to 4 times of potential of the small plate, one of its corner. And then again, if we take ratio V naught by Vc, this will give you 2. So both the process will give you same answer. But if this problem is asked any kind of competitive exam, so I will suggest to use the second method. And this will be valid for not only this for square plate, it will also be valid for 3-dimensional. Like if we have a cube, and if this cube carrying a uniform surface charge, uniform volume charge density, and they ask what will be the potential ratio at the center and one of its corner, you can solve this problem and you will get the same result. So I hope this is understand to everyone. I have tried to explain each small step. Still, if you have any doubt, you can leave a comment. I will try to reply. So thank you. See you in next video.